Okay, guys, so this lesson is talking about extrema on an interval. So if you think about extreme values, that means like super high values or super low values. So this one is talking about maximums and minimums. That's what extrema are. So one of the theorems that we're going to talk about is the extreme value theorem, which is right there. It says if the function is continuous on a closed interval, so that's really important, then the function has both a minimum and a maximum on that interval. So let's look at these as kind of an example. So this one is talking about the closed interval from -1 up to 2. So from -1 up to 2, we know it's closed because there's closed dots. So there is a minimum value right here, and there is a maximum value right there. Those exist. Now this one is a continuous function. There's no holes or jumps in this graph, but there are open dots on the ends. So this is on an open interval. That's a problem because I can't say that this is a maximum. So like, could we say that the point right before that open point is a maximum? Yes, but according to the extreme value theorem, we can't really prove exactly where that is at. So all we can say is that there is a minimum right here, but we cannot say that that's a maximum. So according to extreme value theorem, it has to be closed dots on the ends, and it has to be a continuous function. Okay, so let's look at this first example here. So example 1 is asking me to find the derivative of these functions over here. So I'll write those down in a second. But they want me to find it at the extrema that they have shown. So they've given me points on these graphs that they want me to look at specifically. So this first one, part A, so I've got two problems here. I'm going to talk about B also in a second, but A gives me this function, and they want me to find the derivative at this point. So the first thing I would do, to be honest, I would probably multiply that through because it seems easy to do. There's no exponent on the outside, so I can just distribute that. So my function is really 9x squared minus 27 over x cubed. So when I do my derivative, I am going to use quotient rule. All right, so low, as is, d high minus high, d low. I was just going to write low as is. So 3x squared. And then that's all over low squared. Okay, so simplifying that gives me 18x to the 4th minus, I'm going to distribute this and the minus sign all at one time. So that'd be minus 27x to the 4th and plus 27 times 3. If you have to do this, that is okay. So 81, and then x squared all over x to the, remember you multiply these exponents, so that'd be x to the 6th. And then I'll go ahead and simplify this also one step further. So 18 minus 27, that would be a -9 x to the 4th plus 81 x squared all over x to the 6th. Now, okay, I can't stand to do this. Let's go ahead and get rid of 2 of those x's as well. So really this is -9x squared plus 81 all over x to the 4th. So that makes it a little bit nicer. So now if I'm looking at this point in particular, all I have to do is plug in a value for x. I don't really care about my y value, I care about my x value. So this would be f prime at 3. So -9 times 3 squared plus 81 all over 3 to the 4th. All right, so that gives me negative 9 times 9. That's negative 81 plus 81 all over 81. But if I subtract those, I end up with 0 over 81. So that's just 0. Okay, so here's what's happening. Let's kind of point this out. At this point, so here's the graph of that function. At that point that they asked me about, which was the maximum, this graph, this function was increasing, and then it flattened out, and then it started to decrease a little bit. So this was its highest point before it started to come back down. So at that point, that's what we call a critical point. That slope or derivative was 0. So that makes sense. This one, so part B, this function is actually an absolute value function. Really defined a derivative of an absolute value function, or I'm sorry, extrema. What I would do is graph it and then just look at the limit of each side. So as x is approaching 0, this is a negative slope, this one is a positive slope going this way. But this right here is a sharp turn or a cusp. That means the derivative does not exist there. So if you have a sharp turn or what they call a cusp, the derivative does not exist in that situation. Okay, the last one they gave me was a sine function. They asked me to find my top and my bottom here. So, sorry. All right, so my derivative, first of all, f prime of x, the derivative of sine is cosine. And they want me to find it, they gave me 2 values to look at. So the first one I'm going to look at is pi over 2. Because they said, look at the point pi over 2, comma 1. Well, in that case, my x value is pi over 2. So I need to find the cosine of pi over 2. Some of you just know that. You have that memorized. Let's say you don't have that memorized. What I would do is check your calculator and make sure it is in the correct mode. So first, let me just type this in the way that it is. I'm going to show you what happens. So cosine of pi over 2. So cosine of pi over, let me use a fraction, sorry. Cosine of pi over 2, like that. And I get this weird decimal. That is not what I want. Instead, I want to put this in radian mode. So make sure you're in radians. That's a big deal. So now let me try it again. Cosine of pi over 2. See what I get. I get 0. So this one is 0. And then let's try the other one. 3 pi over 2 was the x value in that one, right there. There was my other one. All right, so cosine of 3 pi over 2, again, I'm kind of hoping you know that, but let's say you don't. Cosine of 3 pi over 2, again, it's 0. Hopefully that is not a surprise to you, because the same thing should happen that happened up here. My function was increasing, and then it started decreasing. So at this maximum point, what happened was my slope flattened out. It should be 0 there. Same thing with this one. It was decreasing, and then it started to go back up. But before it did, when it started to change directions, that slope should have been 0. The slope of the tangent line, I should say. Okay, so that's the basic idea of what we're talking about today. We're talking about these extrema in this lesson and when that's going to happen. So what I want you to think about in the long run is extrema happen when the derivative is 0. So when the derivative is 0, I end up with a maximum or a minimum point. And then I can check and see what's happening around the graph to know, is it a maximum or is it a minimum? So this whole chapter we talk about, when is this function increasing, when is it decreasing? And then we can kind of figure out where those extrema are. We can find out a lot about a graph based off of that. So the last thing I'll mention is here's that idea again of a cusp or a sharp turn. the derivative does not exist there. If it's smooth like this, that's where you've got that horizontal tangent line. The slope is 0. So let me throw this definition out there. The definition of a critical number. So you've got this function. You have that the derivative of that function at this point, C, is 0. So let's say it's this point right here. Or if f is not differentiable at c, then c is a critical number. So either of these cases, they're calling that a critical number. So they're saying if it doesn't exist there, or if the slope is 0 there, that's considered a critical number, which basically just means something weird is happening there. My graph is changing directions, so I need to see what's happening. So if it's a critical number, we have to check out what's happening at that point. All right, so then this theorem, relative extrema occur only at critical numbers. So they're saying you will only have a maximum or a minimum at a critical number. Now notice they called it a relative minimum or a relative maximum. So the reason why they talk about it in that way is because relative means it's somewhere inside this function. If you just have an endpoint like this or this, those could be minimums in this particular case, but they're not necessarily critical numbers, because if I'm just stopping it on an interval and saying, I think this interval is all I'm talking about, that function continues to go on. I wouldn't necessarily find that critical number when I'm working with the derivative. But in the graph, I could say, well, these are endpoints. So those are minimums and maximums, but the relative ones are the ones in the middle that we are talking about. Okay, so I'm going to stop there, and we will talk more about this situation, about finding those extrema on a closed interval in the next video.